Speed is distance divided by time. Velocity is displacement divided by time. Distance is the actual path you travel to get somewhere. Displacement is the straight line distance that between your final point and your initial point. Does not care about the path you took. So then velocity also doesn't care about the path you took. Speed does. I gave you a couple examples, and I gave you this fictional world or country. And then I gave you 5 paths I wanted you to follow. I wanted you to find the distance traveled, the magnitude of the displacement, the average speed, and the magnitude of the average velocity for each one of those. I heard some good discussion already while I was looking for your attendance question. That sort of exactly typifies the problem that so many people struggle with when you first start studying physics, because it's the battle between what you believe to be true and what seems reasonable to you, and the definitions that I give you for specific things that you just need to kind of accept. And so thank you to the 2 gentlemen who are modeling that fantastic discussion for me. Distance actually follows the path. And because speed is dependent on distance, speed is distance over time, speed also depends on the path you take. Velocity is just the straight line distance between where you started and where you end. It does not care what happens in between. So for example, if you're looking at path 1 from actually we did that one in class. If you're going to do number 2, from Strasbourg to Quatsoy to Glerknor to Zorkbaum, displacement and velocity doesn't care what happens in between. It just says, okay, well, you started in Schwarzbaum, you ended in Quatsoff. Nope, you ended in Zorkbaum. It doesn't care what path you took to get there. You just need the straight, displacement is just the straight line. And then velocity is just whatever that length is divided by the time it took you to get there. That is the definition of velocity, even though perhaps it doesn't seem reasonable to you because you actually walked the road. Velocity does not care. And so the values you should have got are going to be similar to this. Your speeds and your distances should be exactly what I got, because we all used the exact same data. We added lengths, we divided by the times that were given for distance and speed, and I'm going to give you those values so you can check your work with mine. But your displacements and velocities may be slightly different because I was measuring with a ruler, you were measuring with a ruler, and depending on how you measured and how precise you were with carrying down to the millimeter is going to change what you got for displacement and then velocity. They gave you a scale here. 1 centimeter is 10 kilometers. So you would have measured it, the displacements. You would have gotten down to the nearest millimeter because that's likely what your rulers did. If you borrowed a ruler from me, I want it back by the end of the block, please. Because we're going to need them over the course of the semester here in class. So these are the values I got. For the first 2 paths, remember D is distance, D with an arrow above it is displacement, V is speed, V with an arrow above it is velocity. And the ones in black here are the correct values. I had to rework because I'm using a different picture than I did last time. Smaller photocopy. So these are the values you should have got for your first ones. Again, the first line and this line here, our values should be effectively exactly the same. It's the bottom 2. You can be out by a couple kilometers, and then your velocities are going to be out by a couple kilometers per hour as well. Yes, Dwayne? How a little bit is a little bit? Like, you rounded. So, like, this one you said was 59, for example? That's fine. Yeah. No, I just did that. I was going to come back and talk about how you would do that. The questions specifically said the magnitude of each. You did not, and I mentioned, you did not need to pull out a protractor and actually take those measurements. This was something I'd done in the past. Don't worry about that. You do not need to pull out protractors. Don't worry about that. So those are the first 2. Comments, questions, concerns on either of those. Are you sufficiently different that you'd like me to check your values? You're talking about speeds or velocities? I don't know the state of the road in this country. I don't know. It also doesn't say what mode of transportation they were using. They could have been biking. Okay, that's 1 and 2. Here's 3 and 4. Again, don't worry about the distance or the directions rather. I didn't ask for those this time. In the past I have, this time I did not. Number 3, displacement and velocity are both 0 because they ended up back where they started. In Ras Is Issa. Comments, questions, concerns on any of those? Here's number 5. There it is. Okay. Comments, questions, concerns on any of this? If you were away or you didn't get it done for whatever reason, I would encourage you, rather than just taking down my values, actually going back and doing the procedure yourself. The answers are in the video. Now you can go back and check it that way. Don't just take down the values. Actually make the effort to go back and see if you can replicate them from the video. So, there are no questions, comments, concerns. Let's keep flipping. So we've got these ideas down. I'm going to do a couple simple examples. We'll see how far we get today. It's modeling more of the same stuff that we've looked at already, just with, you know, some picky details. So average velocity, here we go. Average velocity from calculations is something we've kind of already have looked at. It's stuff that we did, you would have done already, looking at that mapping or map activity I gave you on Friday. But we're going to go through this and look at some picky details. The most important things in physics calculations when you're actually doing this with raw data is to make sure that your units actually match. You have to take the time to make sure that what you're looking at makes sense consistently. It showed up in the review you guys were looking at when in one of the sig fig questions on the review I gave you for your last test. There was a question that had you adding centimeters to millimeters, and so you had to convert one to the other. It didn't matter which one you did, whether centimeters to millimeters or millimeters to centimeters, before you did any of the adding. If you didn't stop and do that, your value would have been incorrect, and some of you did that. Some of you just said, okay, well, 55 plus 9, or sorry, 5.5 plus 9 is 14.5. What? Right? Okay, so when you're looking at these things, so for a couple examples here. In the first one, I've got meters, I've got seconds. If your distance is in meters and your time is in seconds, then your velocity obviously has to be in meters per second. This value comes from these two, and so your data's got to be consistent. If I have something, a distance or a displacement in kilometers, I've got a velocity in kilometers per hour, then the time needs to be in what units? What's the only unit that makes sense there? If I've got kilometers and kilometers per hour, then this 2 represents how much time? It's 2 hours. If I've got a time in minutes and a velocity in meters per minute, then this displacement is going to be in meters. Whatever units you have need to be consistent throughout the question. If I've got kilometers and kilometers per day, then this 1 represents a day. And if you're only going 10 kilometers in a day, I don't know what you're doing. It's very slow. If the units don't match, we need to convert, which we looked at already in the first chapter, just actually making the point of going ahead and doing it. The conversion from meters per second to kilometers per hour was what? How did we convert? Sorry? Both of those things. The value was 3.6, and I can prove it to you again if you want. But remembering this value of 3.6 is important. Going one of the ways we multiply, the other way we divide, which is which? Okay, Kai.
You prove it again.
Sure, let's do it again. So here was the conversion. Let's say I was starting with 10. Actually, let's go 100 meters per second. And I want to convert that thing into a kilometers per hour. I mean, if you stop and think about what this would actually mean, it will start to it'll start to trigger what the correct operation would be up here. So let's talk about this cognitively before we actually go ahead and prove it. If we're going 100 meters per second, what does that practically mean? It means in the time span of, you went the length of a football field every click. Yeah, there we go. That's a second. Every second, you're going the length of a football field. Now, I would hope you would understand that to be very, very fast. So if I'm going from meters, just based on that idea, the value for the kilometers per hour, if you're going a football field every second, should that value for as a kilometer per hour be larger or smaller than 100 meters per second? Just on your understanding of traveling a football field in a second. Should be much, much larger, yes. So if it's going to be much, much larger, then the conversion from meters per second to kilometers per hour should probably involve what operation? If we want to make this value bigger, and we're going to use 3.6, it should be multiplication. To go that way, we should be multiplying. Kai wanted to prove it, so let's go ahead and prove it again. I'm at 100 meters per second, and the conversion method that we used, I called it the factor label method, and it involves multiplying a bunch of fractions. So I've got, Kai, which one do you want to do first? You want to get rid of the seconds first or the meters first?
Meters.
Okay, so if I've got meters on top, we're going to put meters on bottom. And I can go directly from meters to kilometers, so we're going to do that. And then the conversion between these things is that 1 kilometer is the same as 1,000 meters. Okay, that cancels out my meters, leaves me with kilometers, and now we're going to multiply by a couple fractions to get rid of those seconds. We can go straight from seconds to hours if you want, but most people don't necessarily know that value. But you do know how to go from seconds to minutes and then minutes to hours. Hoping you were taught how to tell time back in the day. So if I've got seconds on the bottom, I'm going to put seconds on top to get rid of those. I'm going to convert that thing into minutes, but I don't want minutes on the bottom. I want hours on the bottom because we're going into kilometers per hour. So then minutes are going to go up top on the second one, and then hours are going to go on the bottom. So that's what we end up with. Our seconds are going to cancel, our minutes are going to cancel because they're in opposite spots of multiplying fractions. And the relationship between seconds and minutes is that there's 60 seconds in 1 minute, and there are 60 minutes in 1 hour. And then this is a nice kind of easy way to see how this is going to go. I'm going to multiply across the top. So it's going to end up being 100 times 60 times 60. And I'm going to divide by all the things in the denominators here. In this case, there's only 1,000. And this is where, Kai, that 3.6 comes from again. Because this object right here, 6 times 6 is 36, so 60 times 60 is going to be 36 with these two zeros. So this piece is going to be 3,600. And then 3,600 divided by 1,000 is going to take that decimal on the end and move it in 1, 2, 3 spots. One for each of those zeros. And so to go from meters per second into kilometers per hour, it's our value in meters per second multiplied, and I'm going to grab another color there, multiplied by 3.6. So 100 meters per second is 360 kilometers per hour. 360 kilometers per hour effectively means a football field every second. And there are street legal cars that can do this. Not in Canada, but in Germany, at least. You've got roads that are designed for this. The Autobahn, or sections of it, from what I understand. So meters per second to kilometers per hour, you multiply by 3.6. So then the other way would just be the opposite operation. You would divide by 3.6. Kai, is that enough?
That is
Perfect. Okay, so remembering that path, or even just making it make sense to you. I mean, I've got a clock on the wall with a second hand on it. If you're stuck in a test and you can't remember, go through that exercise I did at the beginning. 100 meters is a football field, and if I'm doing a football field, every tick of that little red hand, we're moving very, very quickly. Because especially those of you who already have a driver's license, or even if you've paid attention as a passenger in a car, you're not going a football field every second, generally speaking, as a passenger in an automobile. If you are, something awesome or terrifying is going on. So then for these ones, it's the same kind of idea. If I'm going 75 kilometers per hour into meters per second, what am I going to do to make that conversion? Someone mouthed it. We're going to divide. So then 75 kilometers per hour, a speed, those of you who have a driver's license, it's a fairly common speed, is going to amount to 20.83 meters per second. Not overly difficult, I don't think. Just again, remembering which way you go here is the only key. You've done a bunch of unit conversions for me already. I'm not going to get you to do a whole bunch more here. You've done this conversion already, going back and forth between days and seconds. I think it was on the first day. I gave you some questions, even like how many seconds and years would it take you to or count to 1 billion? You've done the math for me here. If you want the extra practice, this section down here, I'm going to call optional extra practice. If you want to go ahead and do it, you're welcome to do it. But you've done all this. I've assigned all this already. If you'd like me to give you answers for that after you've gone through and attempted it, we can. Let's actually apply it, though, into the questions that we're going to look at. So if you want the extra practice, do this. Otherwise, we'll move on. Here we go. You've done the distance conversions already, too. In the individual questions that I gave you in the first unit, you've done all of these conversions. We've gone through these things step by step, and as long as, or if it goes through the meter, that base unit, the conversions were really quite straightforward. It just gets more interesting when we go into something else. So I'm just going to do one example here. I'm going to do this guy here, except I'm going to change the question. Instead of 12 kilometers into meters, I'm going to go 12 kilometers into millimeters and just demonstrate the procedure again. But you've seen it all already once before. If I'm going to go 12 kilometers, I'm going to use the factor label method, and I'm going to multiply this thing by some fractions. Now, because I changed the question and instead of kilometers into meters, I'm going to go kilometers into millimeters. When you're using the factor label method, in metric units, you've always got to go through whatever that base unit is. So here the base unit, if I've got a kilometer and a millimeter, the base unit is whatever that unit is that doesn't have the prefix. So in this case, it's the meter. So to go from kilometers to millimeters, I need to go from kilometers into meters, and then out of meters into whatever unit we're looking for. So in this case, I'm going to put kilometers on the bottom of the first fraction. This is going to cancel out those units, if you recall. It's going to put it into meters, because if you have something on the top and in the numerator and on the denominator of a fraction, they're going to cancel, because they're going to divide it, give you 1. Same thing here, my meters are going to cancel. I'm going to put this thing into millimeters. Before I make a big show of canceling these things, I'm going to put in the conversion factors here. Now, again, I'm going to demonstrate this twice, because there was some of you who were Put the millimeters up here, put the meters down here, who are still struggling with where do I put what values when I'm dealing with these conversions. And so there's again, two ways to think about it. If you're gonna use kind of your common knowledge here, you could say, okay, well, kilo means 1,000. So if I wanted to replace kilo, so 1 kilometer, that word kilo I would replace with, if you look at your formula sheet, the scientific notation for that was 10 to the 3. So effectively what I'm doing is I'm taking this k, and because it's not up here in the first fraction, I'm replacing it with that value. So in this case, either 10 to the 3, which is what it would say at the bottom of your formula sheet, or you would remember just, okay, well, kilometers 1,000 meters, if you've done that conversion enough. It doesn't matter if you choose to use the scientific notation or not. And then it's this last step where things become more interesting. If I've got, okay, I want to take millimeters and I want to put them into meters, well, I'm going to go 1 millimeter here, and I'm going to say, okay, well, I'm going to replace this prefix milli with whatever that prefix is worth on the bottom of your formula sheet. Milli, the value I gave you for that on the bottom of that formula sheet is 10 to the negative 3. So I'm going to replace milli with 10 to the negative 3 if you're going to use that scientific notation method. If you're going to do it the other way, you're going to say, okay, well, if you don't want to use that scientific notation way of thinking about it, you'd say, okay, well, millimeters and millimeters and meters. Yeah, okay.
Shouldn't you just have 10 to the 3 on the bottom?
No. Because if I had 10 to the 3 on the bottom and I had 10 to the 3 on top, they would cancel. And I would say that 12 kilometers is equal to 12 millimeters, which is definitely not the case. We're talking about the top one here or the bottom one here? This guy?
Yeah.
Remember, milli is equal to 10 to the negative 3. And then how you're actually using it is you've got a millimeter. Milli means 10 to the negative 3, so I'm not going to put that there. So I'd have to put the value for milli, that 10 to the negative 3, down here next to the meters to replace the fact that that milli was there, is one way to think about this. If I put 10 to the 3 down here, I'd have one in the numerator and the denominator, they'd cancel. We wouldn't want that.
Yeah, it just is. Easy because it's going to switch the top.
And then it's going to become 10 to the positive 3, and it's going to give me a huge value, which is what we want. Because 12 kilometers should not be 12 millimeters. 12 kilometers should be a crap ton of millimeters. So then the last piece, another way to think about it, if you don't want to use that prefix way of thinking about it, the way that I would put this together is I would say, okay, well, I know I put meters and millimeters here, but I actually want to go through centimeters. And I know that on a meter stick, there's 100 centimeters. And I know that on a centimeter ruler, there's 10 millimeters in a centimeter. So if there's 100 centimeters in a millimeter and 10 millimeters in a centimeter, I know then that there is 1,000 millimeters in 1 meter. It doesn't matter which way you choose to rationalize it, you need a way to rationalize it. And then both of these are going to give you the same result. So as Kai was saying here, I've got a negative, you're going back and using your exponent rules from grade 10. I've got a negative exponent here in the denominator, so I'm going to pop that up to the numerator, and I'm going to make that exponent positive. So this is going to become 12 times 10 to the 3 times 10 to the 3. This guy jumped up here, and the exponent became positive. And if we use our exponent rules, then these two are the same base, so I'm going to add then these two exponents. This is going to become 12 times 10 to the 6, which 10 to the 6 is a million. So then this value is going to become 12 million, which if you think about what that means, 12 kilometers is 12 million millimeters. That makes sense. Millimeters are very small. 12 kilometers is very big and need lots of small things to add up to that one big thing. Or, again, you could jump straight to here, depending on how you rationalized it. And then multiplying by 1,000 is easy. For every 0 here, I just tack on a 0 to your answer. So this one, multiplying by this 1,000 is going to give me 3 zeros. Multiplying by that 1,000, it's going to give me 3 more zeros. And at the end of the day, kilometers cancel, meters cancel, and I've got 12 million millimeters. The result is the same. It doesn't matter how you choose to rationalize it. So pick a way and roll with it. Now, I'm not going to be giving you questions like this. Again, the practice down here, if you'd like to do it again, if you're still struggling with this stuff, that's fine. I'm going to call these couple questions here optional extra practice. And we're going to go down and we're actually going to shove this conversion thing. We're just going to make it part of our problem solving. So if you'd like to do this for extra practice, by all means, go for it. I can give you the answers for that, but here's what we're going to do now. I mentioned this briefly, and I'm going to formalize it here. When you guys are problem solving these things, there's a set of steps that I want to see. And there's always students, I had a handful first semester, I have a handful every year, who are like, no, I am not going to do it the way you want to do it. And then as the semester goes on, they at the beginning, they're like, well, this is a lot of extra work. It's going to take me more time. I don't want to do the work Dawidoff wants me to do. And then when life gets a little bit more difficult, and they're, halfway through the semester, or maybe it's not till next year, where they're like, okay, I'm in the middle of Physics 12. I don't actually know how to tackle this problem because you're not using the methods that I'm trying to show you. So I'm going to show you a method. It's going to look redundant because the problems are easy to start, but this is a method I want you to use. It's not overly difficult. But it's work. And so this is what I want to see. When you're given a problem, whatever the problem is, I want you to list all the givens and the unknown variables. I modeled this for you already. I'm going to formalize it here. This list I want to see for whatever concepts are listed in the problem. We haven't even got to talking about acceleration yet. But for whatever concepts are listed, give me those values. Sometimes, I'll say down here often, this will be on a diagram. Not always, but sometimes we will just put these values straight into a diagram that we've drawn to help us understand the problem. Sometimes it's necessary, sometimes it's not. Once you've done that, you're going to write down whatever formula we're going to use. We're still dealing with this first formula, but whatever formula you're going to use is going to come from this information. As soon as we start talking about acceleration, we're going to jump from one formula to 5. And then the formula that you choose to use is going to come from the information that you've been given. So you're going to list your values. Sometimes it's going to be on a diagram. You're going to pick the formula that is most useful for solving this thing. You're going to plug in the numbers. You're going to solve the things, and that's what you're going to get graded on. So if I'm going to model this method on this first problem here, it's a simple problem. What is the average velocity of a dog that runs 45 meters north in 5.5 seconds? Some of you could sit there and do this in your head, especially if I took this and I made it 5 instead of 5.5. If I made this thing 5, the answer is obviously what? Sorry? 9. But it's 5.5, so I've made it one extra step. It's a little bit more difficult, but Kaylin just did it without writing down anything I asked her to do. So I want you to do it anyway. Let's model it. The average velocity of a dog that runs 45 meters north in 5.5 seconds. First step I want to see is you to write it all down. We're given 45 meters north. That's a displacement. Include units, include directions. We've got a time, that's 5.5 seconds. And then often the last thing you'll list is, I want whatever we're looking for. I want to know what the velocity is. That list should be there. And there's no changing directions. I don't have to draw any pictures here. This is an easy one to think about, I think. And now we're going to write down the formula. If you recall, looking at there's only one that I've given you. We had the definition for velocity was this. Velocity is equal to a displacement divided by your time. And so now I'm going to go ahead and plug all these things in. Velocity is going to equal 45. And now in the plugging in process, I'm not necessarily going to include my units and the direction. I'm just going to plug in those values, and then I'm going to bring those units and directions back at the end. I've got 45. I'm going to divide that by 5.5. I'm going to plug that into my calculator, and it's not 45 and 5, which would be 9. It's 45 and 5.5, which is going to be what? What's 45 divided by 5.5? 8.18 repeating. Okay, so let's just call that 8.18. And now let's go back and put in the units, and because it's a velocity, it also needs a direction. All of that just comes from right here. Because I divided these things, it's going to be meters per second, and the direction is going to be north. And for that, on a test or a quiz, or you could write it as 8.18 meters per second with a big letter N inside a set of square brackets. Either way is a totally acceptable way to give your direction. This would be 1, 2, 3, 4 marks on a question like this. And so my physics tests are often out of an absurd amount of marks because I hand out marks for everything, which is actually going to save some of you. If you ever forget conceptually what to do on something, you can get a lot of marks just by writing down what you know and giving me a formula. If that's all you can do, you're still getting 50%. You can pass, technically you can pass all of my tests, 50% is a pass, without actually solving anything. You just need to follow the steps that I've given you as far as you can take them. So flip the page, let's do a couple more examples, then I'll let you play with it. Here you go. We're not going to do all of these because, again, some of them are redundant. Like number 2. Number 2 is redundant. It's effectively the exact same question we just did. What is the average velocity of a person who runs 21.1 kilometers in 2 hours? Because it starts with what is the average velocity, we've effectively just done this question. The only difference between this question and the previous question are the units and the fact that there is no direction given here. So I'm going to skip this one. We're going to go down and look at number 3. Number 3 says this: if a ball is thrown 25 meters per second down, what is the ball's displacement after 0.65 seconds? Now this one is a little bit complicated here, just conceptually, because what happens when you throw an object down? Well, forget that part even. Emma, gravity. And what does gravity do to things? It accelerates them, it pulls on them. And so, because we haven't even talked about an acceleration, and there are ways to calculate it, and we're going to look at how we do that. It's a seemingly simple concept, but we're going to go through the formalization of putting it all together. If I give you a question that looks like this at this stage, if a ball is thrown at 25 meters per second downwards, what is the ball's displacement after 0.65 seconds? What do we have to effectively ignore here? Acceleration, so that we have to ignore the pull of gravity, which makes no sense. But we're gonna pretend gravity doesn't exist for a moment, and we're gonna go ahead and figure this out. So write down everything we know. V is equal to 25 meters per second down. What is this ball's displacement? So that's what we're looking for. After 0.65 seconds. So this represents the time that we're going to use in this problem. So I've got 0.65 seconds. So now we're going to go ahead and we're going to use our formula to solve this thing. Now, I've only given you one. I said, okay, well, velocity is equal to, is defined to be displacement divided by time. But if you take a look at your formula sheet, do I give you all of them? No, I don't. I only give you that one. So technically speaking, we're starting from here. If I've got a velocity, a displacement, and a time, this is the formula we're going to use. And if you don't know any better, now we've got to fill this thing in and roll with it. But how many of you have seen this? That triangle. Hands up high if you've seen that triangle. Often math teachers will show you this because we like to get away from having to solve all of these things. So if you have seen this before, by all means use it. The only thing I'm giving you on your formula sheet is this guy. But there are technically 3 formulas that relate velocity, displacement, and time depending on what you're looking for. If you've never seen this triangle, it's an easy one to memorize. Here's how it works. If you're actually, and that it's easy, it works, but that's the wrong, no one corrected me. That's the wrong triangle. V goes down at the bottom, D goes up top. That's the triangle. And here's how it works. You cover up what you're looking for, and then what remains is going to be the formula. So if I was looking for velocity, I would cover up velocity, and then velocity would equal the thing on top divided by the thing on bottom, d over t. That's the first formula I gave you, the definition for velocity. But we're not looking for that, we're looking for d, and so I'm going to cover up d, and because these two are next to each other with no symbol between them, what mathematical operation is between two variables with no symbol? Multiplication. So then this is the formula we're going to use. Displacement is equal to velocity times time. And really all we've done is shortchange isolating for a variable. If I wanted to isolate this formula for displacement because I'm dividing by time, I'd have to move that up by multiplying by it, I times by time, I times by time, and I would get that d equals v times t. There's shortcuts to all of this stuff. But this is the formula we want to use because d is what we're looking for. So then let's just plug in now these values. Velocity is 25, time is 0.65. So ignoring gravity, what's the displacement of the ball that we just threw in 0.65 seconds? Sorry? 16.25 meters per second down. Do we need the per second? Why did you give me a per second? You don't know. What are we looking for? We're looking for a displacement. Displacement is what units? The direction, and which, do I need meters per second? No, meters per second would be a velocity, so we don't need that seconds down there. This would just be meters. You gotta make sure that as you're approaching these things, whatever the units that relate to the concept are the ones that you're using. I'll do one more of these things formally. Let's do number 4. Do I want number 4? No, I don't want number 4. I am going to you know what? Let's do 4. Yes, let's do 4. Here we go. Next one. Stop me at any point if you've got questions. I got 2 people paddling a canoe, 450 meters at 2.5 meters per second. And again, the language here, like we're stripping out some of the language. I'm starting to talk more, the questions are starting to sound more kind of colloquial, how we'd actually talk about these things. And you need to identify the concepts based on the units that are attached to those values and the English language that's surrounding them, which is a struggle, or can be a struggle. If 2 people paddle a canoe 450 meters at 2.5 seconds, what does that mean? Yeah, Kai. So then this value here represents what concept? Velocity. V is 2.5 meters per second. They've paddled a canoe 450 meters, so that's the displacement. And how long? How long is time? How long something takes is a time. And it might seem unnecessary that I have to say that, but I've been teaching this for a long time and I'm choosing to say it, so clearly it's not unnecessary. And so I'm going to use, it's the same thing. I've got no acceleration here. I've got a velocity. I've got a displacement. I've got a time. And so now I need the formula that relates dv and t, but has solved for time. Yes? It's effectively both. I mean, I haven't given it in this particular question, it doesn't matter which concept you choose to use to think about it, because there is no change in direction. But sure, you could talk about it as being a distance and a speed instead of a velocity and a displacement. In this one, it doesn't matter. So then I want to figure out the time. Now you could start with v equals d over t, this formula we started with right here, because that's the one that I've given you on your formula sheet. But if you remember how to use this triangle, you can shortcut the whole kind of algebraic process. Because if I wanted to use the algebra, t is down there on the bottom, then I'd multiply it up top. But I don't want this. I want to isolate for t. So to get t by itself in this formula, what would we have to do? I'd have to divide by v. And so I would divide both sides by velocity, and I would move that down, and I would get t equals, or your time, is equal to your displacement divided by your velocity. If you don't want to do the algebra every time, this is a tool you can use. To use it, you would cover up the thing you're looking for, in this case time, and you would say that d over v is equal to t, which we have here already. So let's go ahead and plug our values in. We've got a displacement of 450. We've got a velocity of 2.5. 450 divided by 2.5 is what? 180. And because that's a time, the units someone said already are seconds. That's it. Questions, comments, concerns? I assure you it gets more interesting. Number 5, we'll do one more example and then I will free you to play. A car travels at 75 kilometers per hour for 25 seconds. How far does it travel? How is this question different than the ones that we've already done? Why would I do this example? What's going to be different? Yeah, because these units don't line up. I've got 25 seconds and I've got kilometers per hour. So as soon as you have units that don't line up, I'm not going to tell you to convert. You need to recognize now when you need to do this. So let's go ahead and play with this. Let's write down what we know, okay? We know that the car is traveling at 75 kilometers per hour. So that's a speed or a velocity. 75 kilometers per hour, and we're given the next 2-3 words is the time for 25 seconds. Now I started this lesson by saying units really matter, and you need to be consistent. That's the first thing we wrote down. These units are not consistent, and so now we've got to go ahead and do some conversions. I don't particularly care how you choose to convert, but you need to recognize that that's what you've got to do. What are your two options here? Yuli, you already said you needed to convert the seconds into hours. We could do it that way. You could take 25 seconds, put that into hours. Absolutely. What's the other option you have for converting? To make this consistent, Brad. Yeah, taking the 75, in this it's kilometers per hour already, taking that whole thing and putting it into meters per second. It doesn't matter which one you choose to use, you have to do either one of those. So let's just do physics by democracy here. Hands up if you would be like, yes, it would make more sense to me to take the seconds and put it into hours. Hands up if that's the conversion you want me to make. 3 of you. How many of you want me to take the kilometers per hour and put that into meters per second? Okay. And then there's a few hands that didn't go up because you don't care. So let's go with the democracy here. You guys have suggested that I'm going to take that kilometers per hour and I want to put that into meters per second. I'm not going to do it the long way anymore. Going from kilometers per hour to meters per second, it's going to involve this number 3.6. Do I multiply or I divide? Ezra says divide. Ezra's right. 75 kilometers divided by 3 kilometers per hour divided by 3.6 is going to give me how many meters per second? Does the 3 repeat or does it go 83, 83, 83? The 3 repeats. Okay, so this is going to be 20.83 repeating. And so at this stage, what I would encourage you to do is not do any rounding until the very, very end, because you've all got, I mean, at this point, you should be comfortable with using your calculators. I've got 75 divided by 3.6 is going to give us this value. And so now we're going to go ahead, we're going to save that in the calculator. We're going to go ahead and use this thing. I want to know how far it travels. So the formula we're going to use for that is that displacement or distance is going to equal, I'm going to cover up D. I've got V and T next to each other. So it's going to equal velocity times time. I can go ahead and plug these values in. The velocity now, I'm going to use this meters per second, 20.83 repeating, times the 25 seconds. And I've got this in the calculator already. I've saved it there. So I'm just going to hit times. It's going to say ants. Your calculators, all your calculators should be able to do this. If you have the calculator, I recommend it. We're going to multiply that by 25. And we're going to get 520.83 repeating. And now, because we converted kilometers per hour into meters per second, and this thing's in seconds, these units should be what? Meters. And you could absolutely leave it like that. You could also say, oh, I'm going to round this to 520.8. Or you could go so far as to say, you know what, I want to round this to 521 meters. Because at the end of the day, 17 centimeters is this much, and it doesn't matter. Because everything is going to be an approximation anyway. I'm not going to tell you to convert it anymore. You need to recognize when is the time and place to do it. If you would have taken 25 seconds and converted that thing into hours, just to show you what that would have looked like if I'd done it that way instead. This is a two-step conversion. We would say, okay, 25 seconds times, I'm going to multiply that by seconds on the bottom, minutes on top, and then I'm going to multiply that by hours on top and minutes in the bottom. 1 minute is 60 seconds, 1 hour is 60 minutes. And so this would have converted into 25 divided by 60 divided by 60. And you would have gotten 0.00694 repeating hours. Yeah. It is almost always better to leave seconds alone and do your conversions with everything else. Almost always. Okay, I want you to do 1 and 2. When you've got an answer, let me know what you've gotten. Try these two. Well, you know what I'm going to do? I'll give you the answers to these things. I'll show you what the homework is, and then you can just go work on it down there. Okay. I'm going to make sure that these are the ones I actually want to assign. Okay, take a picture of both these pages. Yeah, so these are the answers for the 2 questions I just assigned. The answers, just so you're aware, the answers are listed along here at the bottom. They're not in order. So whatever you find up here, yeah, and it might not even be exact. Like it might be your answer for this one might be 8,970. You need to recognize that rounding that thing to 9,000 is a totally acceptable way to do that. The answers will actually, and the rule is the answers will always be to the correct number of sig figs, which means you should be able to round to. That first question there asks for speed and velocity. So the only difference between speed and velocity. You've got values, let me know what you think they are. I have that.
meters east. 0.45 hours.
It's looking for velocity. Those are the wrong units.
20 meters speed.
It's looking for speed or velocity. The meters are the wrong units. Careful, those are not the same thing.
Meters per second.
Those are 60 hours, 60 minutes in an hour. 0.45 hours.
I just put meters.
It's going to be just under 30 minutes. You could leave it as 0.45. I left it as 0.45 hours. 0.45 times 60.
Oh, shoot. My fault. 20 plus 20. 20 minutes. Third. 1/3. 0.3 hours. Everyone do that. I don't know. How do you convert? Traveling 20 meters per minute.
It's a weird unit. You don't often think of moving in meters per minute, but it's
We're good, kid.
meters per minute.
May I use?
Give me 1 second and then you can go. Okay, so lots of you guys are just, the math is not complicated. It's the devil, the phrase is the devil is in the details, and that is, in physics, that is so often the issue. The math is not going to be overly difficult for the vast majority of the semester. The devil is in the details. So some of you guys left it as 20 meters per minute. Totally acceptable. As long, I mean, this is a unit that makes sense. It's a distance unit divided by a time unit. For speed and velocity, that's what you want. You want a distance unit or displacement unit divided by a time unit. Meters per minute is acceptable. Some of you didn't want to leave it like that. Lots of you left it as meters per second. And again, I don't care which way you post this. 0.3 meters per second or 20 meters per minute, equivalent. Number 2, I put number 2 on here, and I'm glad I walked around and took a look, because I want to be really clear how you convert. So the value you're looking for is 0.45 hours. If you just use this as it was, because that's kilometers per hour, and that's in kilometers, you would say, okay, well, if I'm looking for time is distance divided by velocity, 36 kilometers divided by 80 is 0.45 hours. And you could absolutely leave it like that. You say, okay, 0.45 hours, that's the amount of time it takes. It makes sense with the rest of the units, absolutely. But some of you walking around, I noticed, don't like thinking in fractions of hours, and that's totally fine. The thing you don't then want to do is tell me that 0.45 hours is 45 minutes, because it doesn't work that way. How many minutes are there in an hour? 60. So if I wanted to take 0.45 hours and turn it into minutes, I'd have to multiply it by 60, not 100. So 0.45 hours is going to be 0.45 times 60, which is actually 27 minutes. Again, I don't care care which answer you give me, but you need to be consistent. Here's what I want you to do to practice this stuff. There's all sorts of little details and ways that I try and mess with you. Here's what I want you to do. Circle these questions. Number 2, and then 6 through 12. So you can skip 1, 3, and 5. 1, 3, 4, and 5. 2, and then 6 through 12. 2, and then 6 through 12. The answers are all at the bottom. They are not in order. And the answers on, if it says Hutchison at the bottom of the page, it means that the answers are actually calculated to the correct, which I'm not asking you to do, but the answers are provided to the correct number of sig figs. What that means is, you might not, if you did all these questions, you might not get a 9,000. But what you would need to recognize is, perhaps you got an answer that was 8,750. If 8,750 to the correct number of sig figs, you wanted to put 1 sig fig, would be 9,000. Your answers should always round to one of these answers on the bottom of the page. Yes. No, I will never ask you that. Beyond the first unit, no, I won't ask, I will not be asking you to give me to the correct number of sig figs. So you could round in different places along the way, and it's my job to recognize and make sure that the procedure is correct. So that's what you've got. You've got 15 minutes to do, which is lots of time. You could get most of these done. Feel free to work with your peers and work together. Hey, what's going on? I'm done.
He's on the top. He's not on the top. Wait. Oh wait, you're right. He's on the top.
In the bin. Throw it in the bin. I don't want to take it from you because I'll put it down and I'll lose it forever.
Yeah, my home isn't jail. It's not next to a guy who stabbed me. I will stab you.
Hey. Willing to do a portrait of him?
Sure.